In this video, we're going to explore the question, what do quantum states represent? What I want to show you is that if we take quantum states to represent equilibria, both the math and the physics it is supposed to represent become more intuitive. At least, I think so. With that in mind, we will draw parallel with thermodynamics and statistical mechanics and see that many of the weird quantum behavior are not so weird. So let's start with something you may already be familiar with. In quantum mechanics, physical quantities are represented by Hermitian operators. Each operator is fully specified by a set of eigenstates with their associated eigenvalues. The eigenstates are the states that we find after the measurement, and the eigenvalues are the values we measure. The measurement process is modeled by a projection, also called a collapse, which takes any income state psi and gives you one of the eigenvector as an output. The probability of getting each eigenvector is given by the square norm of the inner product. Good. Note one thing, the probability of transition does not depend on the eigenvalues, just the eigenvectors. Suppose we measured O to the third power, the eigenvalues would change, but not the final states, and the probability of transition wouldn't. That would correspond to the same process, the same projection. So let's remove the dependence on the specific of the observable. So the process is fully characterized by a set of possible final states, which must be all orthogonal to each other. The probability of transition is given directly by the initial and final states. So we took away the measurement part of the process, we simply have inputs and outputs. So we have your standard black box process. Now these projections have a feature. If we repeat the process, the inputs are eigenstates, and if the inputs are eigenstates, the output will remain the same. Now, how do you call a state that remains unchanged through a process? An equilibrium. Eigenstates are equilibria of the projection process. All the outputs are eigenstates, all the outputs are equilibria. Therefore, a projection is a black box equilibration process. Takes any input state and spits out final states that are equilibria for that process. Now let's do the converse. Suppose we have a black box equilibration process. That is, suppose we have a process for which we know the input and the output map, and that all possible output states are equilibria for that process. Then we know that if we repeat the process twice, we have the same result as running the process once. The process is idempotent. If we start with a probability mixture of states, say 20% in this state and 80% in this state, we expect the process to give corresponding output with the same probability. In other words, the process is linear. So the operator that would model this process is linear and idempotent. But that's exactly the mathematical definition of a projection. It is a linear and idempotent operator. So projections and black box equilibration processes are the same thing. Every projection is a black box equilibration process, and every black box equilibration process is a projection. There is no distinction. So I want to encourage you not to think of projection as measurements, but as black box equilibration processes, processes for which you know only the inputs and the outputs, which are very common in science and engineering, whose outputs are all equilibria. Since a measurement must be repeatable, it must yield the same value on the same object twice. Measurement processes are idempotent and linear, they are projections as well. In the same way, a preparation should do nothing if we already prepare the state we want. So also preparations are idempotent and therefore projections. So black box equilibration processes are suitable for measurements and preparations. They can be used to prepare or measure a system, but the process exists independently of their use, state in, state out. The interesting thing is that in the framework of quantum mechanics, all quantum states are the output of a projection. Suppose we have a state psi, we can define the operator OR, which is psi cat psi bra. Psi is an eigenstate of this operator and corresponds to the eigenvalue 1. All other eigenvectors correspond to the eigenvalue 0. This is sometimes called the indicator operator that gives us 1 if we find psi and 0 otherwise. Since psi is an eigenstate of O, it will be an equilibrium of the process characterized by this projection. Since we can do this for every state, all quantum states are equilibrium. To be clear, they're not all equilibria of the same process, they are all equilibria of some process. In fact, if two states are not orthogonal, they cannot be equilibria of the same process. And that's exactly what gives us the unusual features we find in quantum mechanics. But does this make sense, or is it just a trick? Well, it does make a lot of sense mathematically. Hilbert spaces are precisely the Banach spaces for which we have projection operators for each subspace. Banach spaces are vector spaces that have a norm and have limits. So once you say that the system have a size, a norm, and you want your state to be closed under linear limits, projections are what give you the inner product. So mathematically, it makes a lot of sense to say that all quantum states are equilibria. Projections are ingrained in the very definition of Hilbert space. Physically, we should realize that to be able to talk about a system and its state, that system has to exist in a stable way for some finite time. It may be very small. For example, a tau lepton has a mean lifetime of 300 femtosecond, so it's more like a metastable equilibrium, but still, for a brief time, the object is stable enough that we can recognize its signature. So in this sense, it makes sense to think of quantum states as states of equilibria. At each moment, the external and internal dynamics have to be such that the system retains its characters. Now let's assume we found this plausible. How is this perspective useful? The idea is that if you buy into it, some puzzles in quantum mechanics have a more straightforward explanation. For example, why aren't all quantities well defined in quantum mechanics? Why are some observable incompatible? Why can't we describe what happens during a projection? Why can we use quantum mechanics to describe objects at different scales? To solve these puzzles, let's look at thermodynamics. Why thermodynamics? Because thermodynamics is the only physical theory that explicitly talks about equilibria and boundaries. So let's consider a volume of fluid that is free to exchange molecules with the outside. That is, it's an open system. We may ask how many molecules are there in the fluid. Clearly, this is a nil-posed question. Since the system is open, molecule will leave and enter the volume. The number of molecules will fluctuate, but at equilibrium, the probability distribution of the particles will stabilize. The equilibrium of an open system does not define a unique number of particles, it defines a probability distribution that represents the fluctuation at equilibrium. And if we weren't at equilibrium, we would not be able to specify a single well-defined probability distribution. Now suppose our system is closed instead. The molecule cannot leave or enter the region. This time, the number of molecules is unique and well-defined. Therefore, a closed system does define a unique number of particles. Now let's go back to our open system. Suppose we want to measure the number of molecules in our fluid. We first need to define which molecules belong to the fluid and which do not. How do we do that? We close the lid. That way, we have a well-defined number of molecules to count. Schematically, we start with a grand canonical ensemble. This is defined by temperature, volume, and chemical potential. We close the lid and wait a bit, which we model with a black box process. The output will be a canonical ensemble, which is identified by the number of molecules, the volume, and the temperature. Note that the number of molecules will not always be the same. It will depend on how many particles were there when we close the lid. So we will have a probability to find a particular number of molecules. Note that P of n describes two different things. It describes both the fluctuations that were happening at equilibrium in the grand canonical ensemble. It also describes the probability of finding a particular canonical ensemble in the final state. The number of particles once we close the lid is fixed in the final state, so it doesn't fluctuate. So the probability distribution changes meaning. It starts as fluctuation within an ensemble, and then becomes a probability distribution over different ensembles. The idea is that this is completely analogous to what happens in quantum mechanics. You prepare a state, an equilibrium, which is described by the value of a particular quantity, say energy. Then you want to measure position. Well, the position is not uniquely defined in an eigenstate of energy, so you change to a state, an equilibrium, for which the position is well defined. And we are going to have a transition from one type of ensemble, one specified by energy, to another type of ensembles, one specified by position. like we had in thermodynamics, where we went from a grand canonical ensemble specified by chemical potential to a canonical ensemble specified by number of molecules. As we said before, quantum states are all equilibria, but not equilibria of the same kind, of the same process. You should think of quantum state as different types of ensembles identified by different quantities. The observable essentially identifies a family of ensembles of eigenstate, like in thermodynamic, mu Vt identifies the grand canonical ensemble. And the eigenvalue identifies a particular one in the family. While in statistical mechanics we have only a handful of types of examples, in quantum mechanics we have infinitely many. But the gist is the same. The conjugate quantities arise because preparing an ensemble and equilibriums means letting some other quantity fluctuate. Note that in both cases we cannot describe the internal of the equilibration process. This is not for some arcane reason. Simply put, we are out of equilibrium. We cannot describe the system in terms of state of equilibrium. To give a full account, we will have to know what are the constituents, the exact interaction with other systems, the law that governs them, and so on. We need to go to a deeper level. To make this more concrete, suppose that we want to describe the dynamic of a water molecule. In what sense is a water molecule an equilibrium? Well, a water molecule is, for example, an outcome of this reaction. You mix two hydrogen molecules, one oxygen molecules, and you get two water molecules and some energy. We can talk about a molecule of water only at the end of the process, and only if, for example, we don't have external sources of radiation that will come and break the water molecule. In this sense, the water molecule has to be in equilibrium. The reaction has to have carried out, and the interaction with the environment should not break the molecule. But what if we wanted to describe what happens during the reaction? Well, that cannot be described in terms of molecular oxygen and molecular hydrogen. We have to describe it in terms of atoms. So we don't describe the state of the molecule anymore. We need to describe the state of the atom of hydrogen and oxygen. We push down the basic constituent. But the definitional problem is similar. We want to describe the dynamics of an oxygen atom. In what sense is an oxygen atom in equilibrium? Well, an oxygen atom is, for example, the output of this nuclear reaction. One carbon atom plus one helium atom gives us one oxygen atom and some energy. Like before, we can talk about an oxygen atom only after the process completed and if there are no other processes that will start right away that would destroy the atom. So again, in this sense, the oxygen atom is an equilibrium of the internal and external forces. And if we wanted to describe the reaction, we still have to discuss it in terms of nucleons, protons and neutrons. Then we have to go one level lower, same problem. The proton can be seen as the final product of a beta decay. We can talk about the proton after the decay and if there are no other strong interactions. If we wanted to describe the internal of the decay, we'd have to do it in terms of quarks and gluons. So what's the moral of the story? Every level of description, the molecule, the atom, the proton, are equilibria of lower processes. We can describe a molecule as a single quantum object precisely because in determined situation, the internals can be ignored. The upper level dynamics decouples from the lower level dynamics. The upper level can be described by only a handful of properties, and this happens if a lower level dynamics is at equilibrium. The moral is that this is unavoidable. It's a requirement to do science. We need to define what matters and what doesn't for a particular experimental setup. So to sum up, my suggestion is that you think of quantum states as equilibria. Projection, collapses, are black box equilibration processes, and the eigenstates are equilibria of these processes. As we saw, one can make a math physics one-to-one correspondence between them. So the connection is solid. It's not you can kind of thinking like that. No, it is that. All states are eigenstates of some operator, so all states are equilibria, but they are not equilibria of the same process. That's the key peculiarity of quantum mechanics. Equilibria also means that lower, faster scale dynamics are decoupled and left undetermined. If you saw my other videos, this is consistent with quantum states being irreducible. They can't describe the internal dynamics. That's where our experimental and theoretical description stops. This view allows us to use parallel with thermodynamics and statistical mechanics to create a more intuitive picture. In a sense, quantum mechanics is the fusion at a fundamental level of ideas from classical mechanics on one side and thermodynamic statistical mechanics on the other. In a sense, it's the mechanics of equilibria. And under this view, at least to me, it makes a lot more sense.